Hello students, myself Dr. Shalu and I am going to take your physics class from today onwards. Today we are going to understand the chapter moving charges and magnetism. So before going to start with this chapter, let us recall what you have studied in your 3 chapters, right? Initially, what we have started, you have started with electrostatic, where we studied about charges which are at rest. After that, you have studied about the charges which are in motion. When charge were in motion, they produces current, right? So now it's a time to study about magnetism. See the name of the chapter, moving charges and magnetism. They both phenomena, these both things, moving charges and magnetism, have direct relation with each other, right? So before going to start this chapter, let us understand why we are studying about magnetism. Why do we study? Why do we see things around us related to this magnetic field or magnetism? There are certain things which we see around us. Normally, if you have magnet and bring some iron nails in front of it, what happen? They all iron nails get attracted towards the magnet, right? So when we are kids, we think that it looked like a magical phenomena, right? But this is not magic. There is a lot of physics behind it, and that phenomena of physics is called magnetism. The other thing which we see is the magnetic needle. I think most of you have already heard about this thing, magnetic needle. This is used to get the navigation for in the ships, to get the direction. Maybe you will see this magnetic needle in your physics lab when this lockdown period is over, right? The screwdriver, the screwdriver you all have seen in your home, right? It has a magnetic tip, so that the job of the screwdriver will get easy, right? I'm saying all these things because I'm trying to tell you why we are study this magnetism. What is the need of studying magnetism? Most of you have already seen electric motors in your home, right? These electric motors are the application of magnetism. You have a computer. In your computer there is a hard disk. In your pen drive there is a chip which is made up of this magnet. In your ATM credit cards there is a strip which is magnetic. So that is why it is very important to study about it, right? And now if we are talking about the weightage of this chapter, you may get 2 marks, 2 question, one having 3 marks and one having 2 marks, and you may also have one long question having 5 marks out of this chapter. So let's start with this moving charges and magnetism. So there is a very close relation between these two things, and Ørsted was a physicist who actually observed the relation between these two. He observed that when a current passing through an open wire, it produces a magnetic field around it. Means if we have a current carrying conductor, then around it, due to this current carrying conductor, produces a magnetic field around it, right? Like if we, this suppose this is a current carrying conductor, and according to Oersted effect, the current carrying conductor produces a magnetic field around it, like around this conductor there at each and every point there is some magnetic field which is produced by this current carrying conductor, right? If there is a current carrying conductor and electromagnetic field produces around it, then this magnetic field have some magnitude, and the magnitude of this magnetic field was find out by these two scientists, Biot and Savitz's law, and they give one law which is called as Biot-Savart law. What they did, they took and they considered a wire like this. This is a wire having infinite length like this, right? And current I is flowing into from this wire, right? This is a wire carrying current I. This is the direction of current in upward direction, and we wish to find out the magnetic field around at any point around this conductor, right? So they chose an arbitrary point here, let's say at P, and they wanted to find out the magnetic field, magnitude of magnetic field. For this, they have divided this wire into many small elements, like this red segment here, DL, and they named as DL, a small element, and the current element of this small element is ideal, and the direction of this current element and the direction of the current is same, and the point where we wish to find out the magnitude of magnetic field is placed at a distance r from the wire, and there is an angle which is theta between this displacement vector and the small current element. And why I have chosen this cross, basically it indicates that field is perpendicular to the plane of the page and directed into it. There are two symbols through which we can represent the magnetic field. When we go ahead, you will get to know about these symbols of the magnetic field, but till now you just remember that this sign indicates that magnetic field is perpendicular. This sign is for perpendicular to the plane of this page and directed into it, right? So according to Biot-Savart's law, the magnitude of magnetic field is directly proportional to current, directly proportional to small element, and inversely proportional to r square. We named this as 1, 2, 3. When we combine these three equations, we have this. In vector form, we have this value of magnetic field, right? Direction of dB is perpendicular to the plane. Which plane? That contain dl and r, right? We have dl and r plane, and magnetic field is perpendicular to the plane, the direction of the magnetic field, right? When we expand this, we have I dl r sin theta upon r cube. R and r will cancel out, and we have dB is equals to mu naught upon 4 pi I dl sin theta by r square. This mu naught 4 pi introduces at the place of this proportionality. So this is basically a magnitude of magnetic field due to small element. See this small element, due to this element we have this magnetic field. But what we have to find? We have to find out the value of total magnetic field around the wire, right? So to calculate the total magnetic field, what we have to do? We have to do an integration, right? So here This is a complete total magnetic field due to the current carrying conductor, and we have to integrate this. So all these things are constant except this. So this is the total magnetic field at point P. See this figure at point P due to the current carrying conductor having infinite length. Okay, where mu naught, the value of mu naught is 4 pi into 10 to the minus 7 Tesla meter per ampere, right? And mu naught is the permeability of free space, just same as epsilon naught, which you have already studied in your first chapter, whose value is this, which is the permittivity of free space. These are some points which very important to remember. So please go through these points once. These are very easy point to remember. What you have to do is you just go through these points, right? So this is a value of magnetic field. This is the value of magnetic field. This is the magnitude of magnetic field due to small element at point P, right? Let us consider a case. We have to calculate. Look at this picture. This magnetic field is also depend upon this theta value, because we have at each and every point around this wire we have magnetic field, right? So there are some point where we get minimum magnetic field, right, or where we have maximum magnetic field, right? So let's calculate the point at which we get minimum magnetic field and at point at which we get maximum magnetic point. So the point which are lie on the axis of the conductor, like this. See figure. If we have to calculate a magnetic field at this point A or any other point, this point C, so what will be the angle between DL and R? Here 0, because these 2 points are lying on the axis. Therefore there is no theta. The value of theta is 0 here, right? If we have theta, if we have 0 theta, that means sine 0 is 0 and we have magnetic field is equal to 0. Therefore at those points which are lying on the axis of the wire, we get minimum magnetic field. And when we have theta which is equal to 90 degree, we get magnetic field maximum, because sine theta is equal to sine 90. If we have theta is equal to 90 degree, since 90 is equal to 1, then we have maximum value of magnetic field. This, just like electric field, magnetic field also a vector quantity. That means it has direction as well as magnitude. Here we talked about magnitude of the magnetic field, so let's talk about the direction of the magnetic field. So how do we calculate, how do we find out the direction of the magnetic field? To get the direction, to know the direction of the magnetic field, we have used this rule, right hand thumb rule. According to this rule, what we have to do, if we have this current carrying conductor and the current is flowing in upward direction, right? So what we have to do, we have to hold this current carrying conductor in such a way that our thumb points in the direction of the current. See this thumb is pointed towards the direction of the current, and then fingers wrap around the wire. This wrapping of finger gives the direction of the magnetic field, right? This is a necessary condition. We have to use our right hand in such a way. We hold the current carrying conductor in our right hand in such a way that the thumb is pointing towards the direction of the current, and wrapping finger gives the direction of the field. Got my point? Okay, so there is two type of direction of the magnetic field. One is inside the two paper and other is outside the paper. This is the symbol. See, now you will understand why I am using this sign for magnetic field. So this symbol is used for the magnetic field which is directed into the paper, and this dot in the circle is used to get the direction of the magnetic field which is going outside the paper, like this, right? Okay, so these are some important points which I mentioned here. Let's quickly go through these points. Magnetic field lines. What are magnetic field lines? Magnetic field lines are the imaginary lines which represent the direction of the field, right? And magnetic field lines are always form a closed curve. Like if this is a current carrying conductor and there is a magnetic field around it, they always like this my finger and my thumb and my finger gives the direction of the magnetic field and around the current carrying conductor. They always forms a closed curve, and the tangent drawn at any point in the field lines. See, if this is a current carrying conductor and there is some circular lines that represent the magnetic lines, and we draw a tangent at any point in the field lines, that gives the direction of the field at that point where we draw the tangent. And they are concentric, they are circular, so they never intersect each other. If they do, what will happen? If the two lines are intersect each other, we get two direction, which is absurd, which is not possible to get two direction of the field. Therefore these lines are never intersect each other. Okay, sometimes we call strong field, sometimes we call weaker field. What are those? So at any place where lines are crowded, very crowded, represents stronger field. Where the lines are distant are called weaker field. A region where magnetic field lines are equidistant and straight represent uniform field. This is a application of what we have studied, Biot-Savart's law. This is the application of Biot-Savart's law. Using Biot-Savart's law, we can calculate the magnetic field due to current carrying ring. See, this is a ring, this one is a ring, and current I is flowing through this ring like this. See, this current I is flowing through this ring. I'm sorry for the drawing. This line is same as this line. Okay, my drawing is not so good, I'm sorry for that. So, and we wish to calculate, this is a circular ring having through which current I is flowing, and we have to calculate a magnetic field at this point P. See here, this point P. So let us consider a ring having radius A. See, this is a radius, and current I is flowing into this direction, anti-clockwise, and we have to calculate a magnetic field at point P outside the ring, which is at a distance x from the center of the ring, right? So again, we have to take a small element like this. We have taken here small element IDL, which is a current element, and we draw at point P. We connect this Q point with P like this. This is x, this is A. Using Pythagoras theorem, we get the value of R, which is equals to A square plus x square, right? This is the 90-degree angle. this angle is phi. If this angle is phi, then what is the angle? What is the angle here? Obviously the sum of the three angles is 180 degree. This is 90, this is phi, so this is also, this is what, 90 minus phi, right? And we have just studied that at every point where we draw a tangent, we get the direction of the magnetic field. Here one point is that, and we have also studied that we get maximum magnitude of magnetic field at 90 degree, right? So from here, from this current element, we draw a perpendicular which is right angled on this line. At this we get maximum magnetic field, right? So we draw this. If this is 90 minus phi, this is 90, what is this? This is phi, total is 180 degree. You can easily calculate by subtracting these two from 180 degree, you will get phi, right? This is phi. Okay, when we have some resultant here at an angle, some angle, what we have to do, we have to resolve resultant in vertical component and horizontal component, right? Like we did here, cos phi and sin phi. That means dB cos phi and dB sin phi, like, and we take another exactly opposite to this Q, diametrically opposite. We have also taken a point R, again a small element at this point ideal, and this is similar geometry is going on as we discussed here, right? So now what we have to do, we have to choose that those components which are responsible for the magnetic field. See here, these two components are equal but in opposite direction, therefore they will cancel out each other, right? So the magnetic field is due to these horizontal components only. We have write each and every step here on these 2 points. You just go through the at each and every point which I had discussed here is also written over here. Please go through this. If you haven't understand what I taught, please go through this point. Still you are not able to understand, please let me know. We will discuss one more time. Okay, so using Biot-Savart's law, which is this, as we have already discussed Biot-Savart's law, which is this. I have already mentioned that we get dB maximum at 90 degrees there, so that is why we draw dB here at 90 degree angle from the current element, right? So we put 90 degree, we take theta as 90 degree, so we get maximum magnetic field. From figure I have already discussed that dBy components are not responsible because they are equal but in opposite direction. They are not responsible for magnetic field, only x components are responsible. So we have dBx is equals to mu naught ideal, this value cos phi, dB cos phi, right? What is the value of cos phi? Right here, cos phi, this is base, this is right angle, this is hypo. So what will be the value of cos phi? Base upon hypo, which is a is equals to a divided by r की value from Pythagoras theorem. We have a is a divided by a square plus x square. Put this value of cos phi here. This is the simple mathematics, right? A by r cube. We know the value of r, which is a under root a square plus x square. Put the value of r here, we get this. But we have to calculate the total magnetic field due to the whole ring, not because of small element, right? So what we have to do, we have to integrate this dBx. All these values are constant. I remain constant, mu naught 4 pi is constant, radius remain constant, the distance at which the distance x where we have to calculate the magnetic field remain constant, right? All these values remain constant, only this will change dl. So, and what is the value of this dl? This dl is nothing but the circumference of the ring. And what is the circumference of the ring? Just 2 pi into radius. So here we have 2 pi into radius. A is the radius. Okay. So final we have magnetic field. Magnitude of magnetic field is this. This is the magnetic field, is the magnitude of the magnetic field for the ring having only one turn. Suppose if we have many turns of this ring, 1 turn, 2 turn, 3 turn, number of turns, n turn. So what we have to do, we have to multiply the n, which stands for number of turns, by this equation, and we get a magnetic field due to a current carrying ring having n number of turns, right? This is very, very important. You may get this type of question from in your CBSE board exam in 5 marks. So please make a note of it. This is very, very important. So, and another case, if we wish to calculate the magnetic field at origin means this x is not there, this x is not there, right? We have to calculate magnetic field at the origin, means this x is 0. So very simple, right? Put 0 at the place of x, right? So we have this value of magnetic field at the origin of the current carrying ring. Students, this is it for today class, and in next class we are going to do some numerical based on this Biot-Savart's law. Till then, please have a look on these notes, right? Please try to understand these notes. If you're getting any kind of problem to understand these notes, please let me know. We will discuss in our coming classes. Okay, till then, stay safe, stay at home. Bye.